So if everyone's okay with it, we will record the session. Hello, everyone. Welcome to the fourth online lecture called the Lunchtime Talks on Extreme Climate. Today with us is Professor Hermann Klug from the Department of Geoinformatics, University of Salzburg. And Professor Klug will introduce us to the Landscape Lab and to all the things they work on in Zegis. So please, without any further ado, Hermann, the floor is yours.
Yeah, thank you, Biljana, for the nice introduction. Hello, everybody. Nice to meet you virtually through this Zoom web conference here. As Biljana said, I'm coming from the Department of Geoinformatics at the University of Salzburg, but I'm originally trained by physical geography and landscape ecology. And within that subject, we all deal with the understanding of relationships across different environmental processes, functions, and structures in the environment. And related phenomena are based on changing environmental conditions, which you can assume, like the wind speed and wind direction. Precipitation is coming to rainfall or not. And within the Landscape Lab, I would like to give you an introduction to. We are measuring, analyzing, interpreting, and processing these phenomena with the help of geoinformatics methods. We are doing a lot of other things at the department as well, and that's what I would like to show you with the following video, which comes after demonstrating the changes which we have in the Landscape Lab. If you just see the picture in the summertime and you see the same picture in the wintertime, you see all the instruments are more or less buried under the snow cover. This is also what we are measuring, for instance, here with the snow height measurement and the snow water equivalent device over here. Okay, so now have a look at
Macroscope,
what we are doing here.
The world through the eyes of geoinformatics. Everyone knows Google Maps. However, geoinformatics is about much more than that. If you need spatial data too complex for the human eye to comprehend, it's a good idea to get in touch with the University of Salzburg's Department of Geoinformatics. They are pioneers in their field and have been extremely successful for the past 3 decades.
Viele Aspekte unserer Gesellschaft sind räumlich organisiert. Das gilt für Rahmenbedingungen wie den Naturraum, aber viel mehr noch für unsere Nutzung von Flächen und Ressourcen. Die Geoinformatik bemüht sich nun, Modelle und Szenarien zu entwickeln, die als Grundlagen für Entscheidungen über Maßnahmen und zukünftige Entwicklungen dienen.
Geoinformatics is an extremely versatile and highly topical field of science. After all, it deals with issues of our everyday lives, from smart solutions for urban congestion problems to the effects of extreme weather.
Die Landschaft unterliegt vielfältigen Veränderungen, meteorologischen Veränderungen, hydrologischen Veränderungen, aber auch menschenbedingten Veränderungen. Im Landschaftslabor erfassen wir diese Umweltbedingungen im 10-Minuten-Intervall und analysieren in Echtzeit die Gefahrenpotenziale, die zum Beispiel von Starkregenereignissen und Überflutungen ausgehen.
Im Zuge der Quantified Self-Bewegung vermessen sich Menschen zunehmend selbst. Das heißt, mit Hilfe von tragbaren Sensoren wie Armbändern oder Brustgurten können Parameter wie Hautleitfähigkeit, Körpertemperatur oder auch Herzratenvariabilität gemessen werden. Diese Daten können wir dann räumlich analysieren und so feststellen, wo sich Leute wohlfühlen, wo sie sich gestresst oder entspannt fühlen. Somit können Städte dann lebenswerter geplant werden und besser an den Bedürfnissen der Bürger ausgerichtet werden.
Durch das Verbinden mehrerer Perspektiven auf Basis der gemeinsamen räumlichen Koordinaten lassen sich systemische Wirkungszusammenhänge erkennen und Informationen ableiten. Im aktuellen Forschungsprojekt GISMO werden medizinische Forschung, Geoinformatik, Mobilitätsberatung und intelligente Transportsysteme zusammengeführt. Das Ergebnis ist eine integrierte Informationsplattform, die zur Förderung gesunder Pendelmobilität eingesetzt wird.
The innovative methods of the University of Salzburg's Department of Geoinformatics are also highly sought after in the implementation of important social objectives on a local, regional and global level.
Wir sind international vernetzt und viel unterwegs. Wir unterstützen internationale Abkommen und Strategien, wie zum Beispiel die Europäische Biodiversitätsstrategie. Mit der Copernicus Academy sind wir auch ganz im Trend der europäischen Weltraumstrategie. Hier geht es um die zivile Nutzung der Satellitenfernerkundung für verschiedenste gesellschaftsrelevante Themen. Wir haben hier Methoden entwickelt, wie wir mit raumzeitlichen Analysen verschiedene Bereiche unterstützen können, von der Umweltbeobachtung bis zur Katastrophenvorsorge und zur humanitären Hilfe. Es werden mittlerweile auch soziale Mediendaten ausgewertet, wie zum Beispiel Twitter-Daten oder Mobilfunkdaten, alle Daten, die einen räumlichen Bezug aufweisen und die eine Spur von menschlicher Präsenz zeigen. Die Hilfsorganisationen nutzen solche Informationen, um ihre Einsätze besser planen zu können und um auch die Hilfsgüter besser dimensionieren zu können.
Geoinformatik ist eine methodische Wissenschaft, die vernetzt und die vernetzt ist. Ich denke, nur so ist Spitzenforschung möglich und Ausdrucksweise davon ist auch einmal im Jahr unsere große Konferenz, die AGIT, mit über 1000 Teilnehmerinnen und Teilnehmern, wo Salzburg zum Schaufenster der Geoinformatik wird.
Students can choose from a wide range of lively, international and practice-oriented courses. Understanding connections, shaping the future.
Das große Privileg, das wir haben, ist, dass wir ein Doktoratsprogramm, ein sehr internationales leiten, wo wir die Doktorandinnen und Doktoranden auch ins Ausland schicken können, umgekehrt Gastforscherinnen und Gastforscher beherbergen.
And I like the master's program. So when the opportunities for the PhD program, I was glad to apply for them. The research questions in the PhD program are also very exciting. So it's a good place for me to be and to study.
Und hier gefällt mir sehr gut, dass es alles so persönlich ist und man die anderen Studenten und auch die ganzen Dozenten kennt.
What I really appreciate about the Master of Geoinformatics in Salzburg is that you now can deal with the problems and questions raised in the bachelor's program in a practical way. So you can build your own applications, you can design your own web maps, and that's what I really like about the Master.
Universitäre Bildung ist nicht nur ein Thema für klassische Präsenzstudenten. Es ist ein Thema für Lifelong Learners, also Personen, die mitten in ihrer beruflichen Karriere stehen und die nach fundierten Möglichkeiten für eine berufliche Aus- und Weiterbildung suchen. Weltweit haben wir heute über 2000 erfolgreiche UniGIS-Absolventen.
Wir bilden unsere Welt in digitalen Modellen ab. Geoinformatik schlägt für unsere Gesellschaft die Brücke von realem zu virtuellen Welten. Diese Verbindung funktioniert nur über die Position, über die Antwort auf die Frage wo, denn ohne diese sind alle unsere Daten im Nirgendwo.
Okay, coming back from the virtual world to the real world, but still we are virtually here. So you have seen, well, we do a lot of things and it seems like in the video that we are separating these things. Of course, we are not separating single things like remote sensing from in situ measurements like we are doing here, but we are integrating them. That's a good benefit we have in our team, that we have people very skilled in Copernicus, satellite imagery stuff, and people like me working in the field. So what we know from landscapes is that the only constant of landscape is change, and changes apply over decades, like we see in climate change, or they apply annually or seasonally, as we have seen before. But as you have seen also from the video, changes are happening in minutes. So precipitation occurs, could be heavy rainfall events, and then something is happening. Understanding the landscape processes, including their functioning and the structure coming out of it, requires information to be captured at a very high timely but also spatial interval. And that's basically what we are doing here. You have seen that station in the video as well, where the camera was moving over the bridge and people were standing in the riverbed. And this project I would like to introduce you to now is sort of was initially founded in 2011 in New Zealand, because New Zealand had the problem that they didn't understand their aquifer systems. So the idea of the project was a 6-year lasting project, was to characterize New Zealand's aquifer system to make an idea what are the existing groundwater volumes, how are they changing over time, and how much water could be extracted and used for agricultural purposes, and managing the water resources was the main subject. And our task within that bigger project was the in situ component, measuring how much water comes to the ground, how much water is infiltrating, how much water is flowing by interflow or leading to groundwater recharge and filling up the groundwater levels. 20 years ago, I was doing research on hydrological processes with a particular focus on nutrient emissions. We were doing so because 20 years ago, we had a problem with our local lake called Lake Mondsee, sort of Moon Lake. And this got under eutrophication. So we had huge algae blooms. And these algae blooms were particularly red algae and blue algae. They are toxic and consume a lot of oxygen from the lake. They reduce the light penetrating through the water and thus changing the aquatic system in a negative way. And this, according to the Water Framework Directive, is not allowed. So we had to search for a solution. And in the beginning, we were just modeling phosphorus emissions in space and time. But the question I received was always, can you verify what you have modeled? Can you underpin that your models are correct? And this requires, for some measurement in the field to underpin that what we have modeled is matching to that what we are measuring. So what we are looking at here is reducing agent in this aquifer system, and this is phosphorus. So there's a lot of nitrogen available, but if you put 1 drop of phosphorus to it, then these algae blooms start. So we had to look at phosphorus emissions, and we had to ask ourselves, okay, when are these emissions taking place? Of course, during the fertilization processes, but are these the ones most important? You can infer from this title, which I put here, that phosphorus emissions mainly result from extreme precipitation events. And that's why we asked our key questions. So which influences occur when? So timely, where, location, how strong, on whom, and or what and why. So the subject as well. So the subject are the lakes. If you call or recall the heavy rainfall events, then of course we also look at humans being impacted through floodings. So what we are doing here is the formalization of spatial and temporal information for multifunctional applications in landscape. So we have, for instance, blue light organizations being interested in for forecasts in flooding of regions. We had the hydrological survey or the tourism agencies interested in the quality status of the lakes and so on and so forth. So the key question is, what impacts do phosphorus emissions cause during heavy rainfall events, and when considering the fertilizer applications in space and time before the extreme weather events. So, of course, we know that the emissions are not only coming from agricultural business, but also from atmospheric depositions, from wastewater treatment plants, releasing a certain amount of phosphorus to the rivers. But the agricultural areas or the emissions from the agricultural areas are the most important ones. So what we are looking at is the question, what is happening after a fertilization process? So fertilizers are brought to the field, and if there's no rainfall, almost all fertilizers will stay on the field. So that is what we expect at day 7, that there's almost no emissions if there's 7 days of no rainfall after the application of the fertilizers. But if you apply the fertilizers and immediately after, 10, 12 hours, 20 hours afterwards, a heavy rainfall event occurs, then 80 to 90% of the fertilizers which have been brought to the field are gone to the rivers, further to the lakes. So that was our assumption, and we were looking at that assumption in a particular area. So you look at the satellite scene here, it's a Landsat scene, false color, where Salzburg is in the left bottom corner. You see that indicators, and you see, or you can imagine that there are a couple of lakes in here. So that is Lake Mondsee, this one here. Then we have Lake Irsee and Lake Fuschelsee. And here is the outflow point, and from the outflow point we could derive always all the highest elevations which make up the surface catchment of that area. So the catchment border outlined in white here tells us how big the catchment is. It is 27 kilometers from east to west and 20 kilometers from north to south, with a very, very dense river network. So every 300 meters, you statistically enter into a surface water body, a river or a lake. So you have very close distances of movements of phosphorus from terrestrial area to aquatic areas. Of course, we couldn't analyze the whole 248 square kilometers, but we have a look at a particular smaller catchment, which is isolated in the Koppel catchment. And from here, we also know that a lot of contributions of phosphorus emissions enter via this red pathway, the Fuschler Ache. The river is called like this, into the Lake Mondsee. As said, the extent is 248 square kilometers. It's also an area which is registered with the Long-Term Ecosystem Research Networks, LTER, which is a representative of the ILTERNet, so International Long-Term Ecosystem Research platform, where we contribute to. And you see, we have rainfall events like 90 millimeters in 24 hours, but I will also tell you about an event of 14 millimeters, which happened in 10 minutes. And you just can imagine what is going on in the area. I will show you some pictures about that. Of course, if you have just a GIS system or a remote sensing system looking at, then you don't necessarily immediately see the relief structure of that area. That is what you can see here from this area picture. And you see that in the southern area, so that is everything which from the middle of the picture goes to the left, is the alpine area. The alpine border is exactly at this border where you can see where the lake is ending and where these hills are popping up. And to the north, we have the Flisch area, which is more hilly, even into the direction of flat. So what you can also see here, that we have a very high relief energy potential. So we have the Schafberg, which is the highest mountain peak a mountain summit in our catchment at 1,782 meters, and just 3 kilometers line of sight, the lake level of 478 meters is allocated. So on 3 kilometers distance, we have sort of 1,300 meters elevation in between. Between the southern part, so the left side picture here, and the north side picture here. And because of that relief structure, our weather conditions are different to those of other areas. So you see in the north, we have 800 millimeters of rainfall, and to the south, there's 1 meter more annually. So it sums up to 1,800 millimeters in the south. So the distribution of rainfall is very different, where we have very high relief energy, we have very high precipitation rates, and where we have flat areas, we have low precipitation rates. So, and now, as I said, according to the European Water Framework Directive, a status of a lake is not allowed to be or to get worse. So we had to find a solution, what is the problem, and deriving solutions out of it. So looking at extreme events. So when one of those extreme events happened, I by accident took a picture from my office in the morning. It was looking like this. And the weather forecast was also like, okay, it's getting worse over the day. This is the picture 2 hours later. And even 2 hours later, this is the situation in the Mondsee catchment. So people got flooded from blue sky, sunny area in 4 hours to a flooded area. So you see, changes are happening very rapidly. So measuring landscape changes once in a while is nice, but particularly in our case study area, it's useless because changes are happening quite fast. So how does it look like in those kind of situations? So we are in an area which has been glaciated in the last ice age. So we are in the ground moraine area. So our soils are very clayey and loamy clay soils. So we have quite heavy soils. They get quite fast saturated. And once the saturation level is reached, you see something like this. The water is coming out of springs at a certain slope and flowing as surface runoff down the slope. So knowing the conditions of the soil moisture and knowing what is the saturation level of a particular soil, and also knowing that the weather forecast tells us, okay, well, in the next hours, there will be 50 millimeters of precipitation in 1 or 2 or maybe 6 hours, then we could easily model what will happen in the landscape. So this could be communicated via an early warning system. If you see the same slope in the winter time, you can already see that there are springs coming out because these are melting the snow, because the water coming from inside of the hill here is warmer than the environment, and anyway water is melting the snow. So we have double the amount of water applying here because the melting snow and the water coming or being released from the slope. This is how it looks like after a few minutes of rainfall. We have local retention basins by purpose. You can see here from this soccer goal, the part of the soccer goal, that is sort of a meadow which is used for soccer playing. You will see that in a later picture. But at the same time, it's sort of an area functioning as a retention basin so that not the streets and the infrastructure is getting compromised. So what is important is that we have not only an early warning system applying to a huge area, to the whole Mondsee catchment, but we need to have tailored spatial temporal information distribution to be provided to people who need it at a certain time in space. So this is what we call proactive disaster management. So being prepared before the disasters coming and not reacting afterwards. So water is fast accumulating. That's because of our very steep slopes and our heavy soils where water is hard to infiltrate. So you see these constructions in the backside and in the front side that, yeah, huge amount of water is coming down here. And for instance, flooding an area where I put later then my my station. The station is located, or I put up the station right here, and you see here the inundation areas. This is a sort of a usual rainfall event here. This is nothing special. So that is how it looks like if it is just a bit of raining in our area. So in June 2013, where there was one of those bigger flooding events, the water level was approximately 4 meters above the ground here. And you can imagine that is in the beginning of water coming together and flowing to Lake Mondsee. And you can imagine what will happen when from the further slopes, even more water is contributing to. So getting back to the slope of origin and looking at the focus we had on our phosphorus emissions. So why we do have phosphorus emissions? The grassland used here is made for cattle fodder, and it's about 4 to 5 harvests annually. So that means all the nutrients being stored in the soil went into the plants were cut, removed, and are now the energy providers for the cows to grow, to provide milk, and to do business out of it. So the business is milk products like cheese, yogurt, and so on, and the meat. So at some point in time, there is no energy within the soil anymore. So there's all the nutrients are gone, so we have to replace them. Replacing the nutrients are taking place with usually liquid animal excrement. So they are sprayed on the grass surface. And now imagine, you know this slope already. There is a quite wet soil. Saturation level of the soil is quite high. We have a heavy rainfall event. And then you can imagine what will happen with the fertilizers put to the field here. So our assumption was that a tailored application could reduce nutrient emissions when we inform the farmers in due time when would it best to bring the fertilizers without losing them through heavy rainfall events. This is how it looks like after heavy rainfall applies on a slope fertilized like you have seen before. So if you look to the books and about soil erosion, they tell you mainly that there's no soil erosion on grasslands. If you just look at the water, the dark water here, the brownish water here, you can imagine that there are a lot of particles flowing down the slope. So we have particle-bound phosphorus emissions. But of course, there's also phosphorus stored in the water, so the liquid part. And now the question is, how much phosphorus is in the water and now contributing to the next river and flowing to the Lake Mondsee? And of course, if you tell that to the farmers, well, they get, first of all, me as a Prussian, being in Austria, they get angry about me, but I'm telling them what they have to do and not to do. But then I asked them, okay, guys, you see what is happening. So we do that exercise. I collected the farmers, I went and brought them to the field and say, okay, now you applied your liquid excrement of your cows to the field, and now you see them running off. And you know your grass will not grow best or in an optimal way because fertilizers are missing. I mean, you are just losing all your fertilizers you just brought out. And then I asked them, okay, what would it cost to replace 1 cubic meters of this liquid excrement manure? And then they told me, okay, it's about 4 euros. So then I asked them, okay, how much of them did you bring out to the field here? And then they just counted the amount of cubic meters and multiplied it with 4 euros. And then they said, oh, we are losing a lot of money. Yes, you're doing. And you're losing a lot of money, you're losing time. Because now you have to buy industrial fertilizers because your cow shit is gone. It's already, it was on the field. So you have to buy fertilizers. You have to take your tractor to the field. So you have to fill up your diesel. You have to pay for the diesel, and you have to spend time for bringing out the fertilizers again. So you're not losing only these 4 euros, you lose a lot of more money. And that was the point where I got them and said, okay, well, might be a good solution that we bring out our fertilizers at times where it is not prone to be gone because of precipitation. So what we calculated later on, that 80% of the emissions could be explained via these heavy rainfall events. So we collaborated with farmers. We told them, okay, how is your underground looking like? We took them to the field, having experiences during those extreme events, but also in sunny environments. And we started collaborating and explaining what is going on here. So we have precipitation, and we have infiltration of the rainfall as long as the soils are not saturated. So we have interflow, we have surface runoff, and we have the discharge through the river, and we have the fertilization process and the phosphorus runoff, mainly through surface runoff. And then we said, okay, what is the status of the soil? We could capture with soil moisture sensors here. At the same time, we capture a temperature, because if the soils are frozen, like it could be in the wintertime, then of course we will have surface runoff in case of melting of snow and precipitation in liquid format, because when the soils are frozen, there is no infiltration. So we could capture the precipitation with a tipping bucket. We have wind speed, wind direction, and a couple of other sensors applied to a wireless sensor network. And this is what I come up with as a structure. So we have a lot of sensors, like mentioned before, at one station. And these sensors are connected to wireless protocols. Could be LoRaWAN, it was not existing in the beginning of 2011. We used Zigbee for that. Zigbee is a protocol like wireless LAN, operating at 2.4 gigahertz and operating 7 kilometers line of sight. So every 7 kilometers, I could be connected to another station to transfer the data sets. So what we did is we stored all the sensor data in a 10 minutes interval at the station, but at the same time we were sending those to one hub also connected to the internet. So this was sort of a mini computer, a Raspberry Pi, at that time 35 euros, collecting all the data from the stations, storing them, either file-based or in a database, which of course through the database, but at the same time, we were sending this information via SIM card to a cloud service. So we stored the data at the cloud, but that's nice, but just storing data is useless because you have to analyze them in real time. And to make them interoperable means that others could also make use of the data set for their purposes. We applied standards, not only for the transmission process, but also for the storing process. So we look at standards from Open Geospatial Consortium, like Sensor Observation Service, observations and measurements as a data format, or water markup language, WaterML 2.0. In New Zealand, with the groundwater approach, we also developed the groundwater markup language, GWML 2.0. So we were involved in developing the standard because at that time we were interested in getting a standardized data format being active on the global level. So the data sets being stored in the standardized format, so you know what is getting in and you know how to get it out at the interface. You could program interface connections from the data sets to modeling environments, like runoff modeling or whatsoever modeling. So there are a couple of existing models, like an opening modeling interface environment, or you design your own model. You know your data standard, you know your model standard, and you just have to connect it. So each time when data sets are approaching at the web socket, another round of modeling approach is immediately starting. You could also connect sensors. If, for instance, one sensor is measuring precipitation, so it was nothing, and then precipitation, rainfall starting, the tipping bucket recorded a few ticks, then it goes to the internet. The internet said, okay, when it will start raining, then the phosphorus device should switch on to measure the phosphorus loads increasing with the rainfall. So the phosphorus device is not measuring the whole time. It would be a waste of chemicals doing that. It should measure when something is happening. When something is happening means when precipitation is starting or when fertilization is starting. Otherwise, the device is silent. Once something is happening, it goes on. Simple measurements, like here in the existing models, are partly hard to interpret. I mean, for us, coming from geoinformatics, from landscape science, whatsoever, we know what we should do with the data sets. We know the meaning of the data sets. But for stakeholders, they don't. They need to have sort of indicators with a flag like green, yellow, red. Green, everything is okay. Yellow, be careful, something could happen. Red, do something, there is something is happening. And these indicators could be transported as tables, as charts, as maps, web maps, where you see spatial distributions changing, whatsoever. But that's, again, not all, because I don't want to sit all the time in front of my computer, watching it and looking for changes, waiting for changes. I would like to get informed via my cell phone when something is happening. I would like to get a message, like an email, a WhatsApp, an SMS, whatsoever, when a particular condition is changing in a direction which I know which is unfavorable. So this system is sending information, tailor-made information. So people like the mayor of our municipality received a different message to those of the fire brigade, to those of the farmers. They need to have different information at a different time with a different subject. And this is what you have to train the system, what has to be done at a certain place in a certain time based on the circumstances. What type of message you provide comes, of course, from the clients. The mayor should tell you what kind of messages he needs to have at which type of circumstances. The same is with the fire brigade, the same is with the farmers. You collect that, you apply that, you ask them, is that the one you would need? They say yes or no, you modify it, and then it's done. So what we have done here is the integrated transformation process from data capturing in the field towards the generation of knowledge and the provision of practical information for decision support. So decision support, which should provide an indication to do something, not just to wait and curling thumbs, but yeah, doing something. So we tested that in a catchment which is 6 square kilometers in size. So the red rectangle under the edge of the catchment, this one here, is the outflow point of the catchment where the measuring station is. We have other supporting stations within the catchment, slightly outside the catchment or a bit further outside the catchment. And these are collecting information. Collecting information, for instance, from cameras. So I installed robotics cameras looking to the landscape. In the winter, I'm interested in the distribution of snow, the snow melting processes, and to see what is the snow condition at my measuring device, the snow height and the snow water equivalent, and what I could see in the field during the melting process. At the same time, in the summer, I could watch the grassland and see, okay, a green area, which obviously has been just mowed a few days before. This is the 28th of June 2016, 2 o'clock. At 5 o'clock, the TensorFlow algorithm put a message to me on my phone, say, hey, there's a farmer on that plot fertilizing your field, or his field. You see the fertilization process in the change of color from the fertilization, and you see vehicles like tractors, and that's where you can train the system on. Looking at tractors or looking at changes in the underground conditions. So this is an indication, again, for the device measuring the phosphorus from the river, switching on, because now fertilization is brought out. It takes some time until these fertilizers will reach into the riverbed where I have to take my samples from. So when I immediately take a sample, the sample is not impacted from this fertilization process. And starting from that, I could tell you what amount of phosphorus is coming to the river based on this particular fertilization process and how much of the fertilizers are gone. That is just one solution, looking with webcams. But the other one is that, you know, fertilization processes has also some olfactoric means, so it stings when the fertilizers are brought out. If we smell, it stings. That means sensors like CH4 or CO2, also ammonium, or these are sort of increasing in level. So fertilization could be found with particular sensors. So we integrated a couple of carbon dioxide and nitrogen dioxide, ammonium and methane sensors. And this was done with a school close to us. So people from a technical school, being pupils shortly before their high school degree, they did a test like this and did it as a sort of thesis in school. So what we could do is we put those measured devices at certain places, and now a farmer is fertilizing a certain field. Based on wind speed and wind direction, we know, okay, are these fertilization ducts transport with the wind towards the station or away from a station? So we measure more or less intense methane, for instance, and from this we could use triangulation process and to infer, okay, this must be the parcel roughly, not on a meter level, but in a certain area where fertilization is happening. And then we see, okay, when the fertilization takes place on this field, it directly goes to the riverbed and reaches the outlet of the catchment in rather minutes than hours. So the forthcoming rainfall event, you can quite easily infer it from this picture. You know, in the northern part, we had 800 millimeters of rainfall. In the southern part, we have 1,800 millimeters of rainfall. And that's exactly what you see here. The northern part is to the left-hand side, where still sun, where's still sunny environment. To the south, you see the dark colors of the clouds is already quite a thunderstorm approaching. And that is also the reason why I put 10 weather stations on 6 square kilometers of size, because I knew from my own experiences at home, where you have seen the slope, where the water was running off the surface, we had heavy rainfall events, and my daughter was horse riding, and I asked her, well, you got really wet today, or? No, it was sunny. This is 2 kilometers distance of my home. And that is exactly what you see here. She's horse riding here, I'm living here, completely different situations. And of course, impacts. So we had to do some weather predictions and observations and monitoring and integrate weather predictions. So something coming up in advance in future with our measurements. So this is what I've done with the Romanian student, because I'm teaching in Romania as well, in Timișoara. So we used the supercomputer in Timișoara to predict the weather forecast, because we already got an idea that there will be a thunderstorm coming, and we just pre-modeled this 72 hours in advance. And I reported our modeling approach to our municipality head, to the mayor. At that time, he didn't believe me. He believed me after 72 hours, because it went to happen. And our prediction accuracy was 83%. So why did we know that? Of course, after the event, we collected the information from all the stations, not only our stations, because that could have been a bias, but also from other stations, and saw and compared that with the predictions. And as I said, 83% of accuracy, 72 hours in advance. And if you imagine 72 hours in advance, you can do a lot. So we compared that with our soil moisture sensors. We put them in different depths. So the first one with the number 1 here is 25 centimeters. The second one is 50 centimeters. The third one is 75 centimeters in the underground. So we were interested in the first almost meter of the soil, and wanted to know about the soil moisture conditions here. The soil moisture conditions from this sensor to 25 centimeter depth at that time was about 42.5 volumetric water content. Our application, you remember from the picture, was on the 28th at 5 o'clock in the evening. And you see here a precipitation event happening. We know from our soils that the saturation level is at 42.5% of the saturation. So the fertilization already took place at a very wet soil, which is also not good because of soil compaction, because if you ride your very heavy vehicles on a wet underground, you have sort of a very high soil compaction. That's one thing. The second thing is that infiltration of the fertilizers into the ground were almost not happening. And then we had that heavy rainfall event. We measured that with our device, measuring phosphorus in different formats, like particle-bound orthophosphate and stuff like that. And this device was located in this box here, had a connection to the river, so we could take samples at any time. It was steered by a Raspberry Pi computer being in here. So this computer received signal from SIM cards, from the wireless internet, and taking sample from here. At the same time, we had discharge measurements, so flowing speed, water level, and with it, the discharge of this river here. And we know at that particular area also the rainfall, the wind speed, and everything in here, and also the groundwater levels. You see, everything is also energy autarkic, because usually if you want to measure something, you measure where there's no power connection, there's no power plug somewhere. So you have to find sort of your own energy provision, which was sort of a quite big hurdle in setting up the station here. So then we recorded information from the event. We had our own measurements, which you can see here. It was Salzburg Airport, which is about 12 kilometers far away. Salzburg Freisaal, it's about 10 kilometers away. Line of sight is 7.5 and 9.5 millimeters, but they are in a flat environment of 435 meters above sea level. In our area, which is about 720 meters above sea level, we recorded 14 millimeters in 10 minutes. It was just push and it was gone. There was just one cloud raining for 10 minutes and then it was done. And you see that also with that peak here. And it was not covering the whole area of our catchment, just one particular area where this cloud was popping up, raining, and then it was done. We observed our discharge device, and you see here the discharge. Oh, there was nothing happening, a bit more, a bit less, but nothing serious. And then there, this 10 minutes rainfall event, you see that we increased the discharge to 2.5 cubic meters a second. So from 110 liters per second to 2,550 liters a second in 10 minutes. So it's multiplied by 23. In terms of water level, so we had before we had a water level recorded from this device by pressure and by ultrasonic sound from 30 centimeters to 69 centimeters, also 2.3 in level in 10 minutes. So this is the picture which you might know from the video. The device recording the discharge is in the riverbed here, and you see here a meter, the measuring device, and you see that the water level. This is the normal one. It was taken the next day. So the next day you don't see anything about what happened in the night. So this is the water level at approximately 30 centimeters. The water level was at this level here, as you can infer from this meter, so 69 centimeter. So at the same time, we measured phosphorus levels. So you see, we have a baseline emission rate of 20 parts per billion. So this is always coming from the underground, so we cannot change it. That is, landscape prone. So it comes from the landscape. During the event, we had measurements up to close to 100 parts per billion. That means multiplied by 5. So 5 times more phosphorus emissions during these 10 minutes of very high discharge. But that is the concentration. Now we have to multiply the 100 parts per billion with 23, because the water load, the discharge was also increasing a lot. And that's why during these particular events, a lot of runoff is taking place. So the phosphorus concentration and load is increasing during a rainfall event. And not only the phosphorus load is important, the one, but you have to include those type of heavy rainfall events into your annual balances. Usually what people are doing when you look up the literature about nutrient modeling, they always apply average conditions. And these are always misleading. So we did this exercise also in other areas, and we could not underpin what this has been done with standardized modeling tools, because the measurements speak another language. So they are different. So looking at different disasters like landslides, which we also have in that area, we could infer those landslides early enough to prevent humans from certain impacts. Of course, not infrastructure. We cannot remove the infrastructure, but we can remove people from an area impacted. We could ask people to protect their basements with sandbags whatsoever, and prepare themselves for those kind of events. And that is also what I'm doing, because I'm living in that area. Maybe that's why I'm doing this research. But in the beginning, everybody was laughing at me. Oh, what are you doing with your sandbags there? La 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 la. Our neighbors twice already had water in their basements. I never had that, because I knew what to do and when to do. And with it, people first laugh at you, then they look at you, and then they ask questions. Please, can you tell me when we should put our sandbags? Just look at me. When I'm putting sandbags, you should do it as well. So that's it. So nothing is as resistant as the dynamic of change, and the challenge, of course, coping with it. Thanks for listening, and looking forward to your questions.
Thank you, Hermann. This was really, really interesting lecture, and the system that you just presented can be applied for different, as you said, for different extreme events. And it would be nice to have something like that here, because here we also are missing early warning system for different extreme events. So if anybody have any question, please just unmute and ask, or you can just write in the chat and I can read the question. Okay, Minut, are you here?
Okay, so I would first like to thank for this fantastic lecture. It was really, really inspiring, and I enjoyed it very much. And I believe that our audience also enjoyed it, because we have many of our students of geoinformatics here present. So I would like to encourage them also to ask questions and to use this fantastic opportunity to talk to one of the leading researchers from the field of geoinformatics in our part of the world, from Europe, most definitely. So I would really like to highlight that your presentation, your lecture was captured the essence of our discipline of geography, of geoinformatics, the dynamics in our surrounding, our environment, and the importance of monitoring these changes, and the importance of multidisciplinarity, that we have to include many scientific fields, climatology, geology, economics, social sciences, and geography is actually the point where all these sciences meet. So really, you did a fantastic job in presenting this research. So I would have maybe a question, and that would be regarding the accuracy of the models that your really impressive field laboratory can achieve. And have you done some studies regarding the accuracy of extreme weather event occurrences and the impacts that these events have in the space?
Yeah, I mean, as I said, this one which we forecasted and observed during the extreme event, we published that also at Geoinformatics journal. And as I said, it was 83% like this, 83% of the accuracy in forecasting the event in advance. Of course, there are always challenges with the initial conditions and the fertilizer applications, how much fertilizers they put to the field, how much you are losing in relation to that. That's not too easy. I mean, the problem is that you cannot talk to all of the farmers at the same time, because the fertilization usually takes place more or less at the same time. So they have more or less equal conditions in this koppel catchment. So we are about 650, 750 meters above sea level. So conditions in these 100 meter elevation difference are similar. So as I said, we have about snow to the April time. And that is also what we observed. I mean, in April, during the snow melting process, we also have a lot of phosphorus runoff. The question is why? Because, I mean, you are not allowed to fertilize on top of the snow. So there couldn't be fertilization processes going on during the snow melting period, or shouldn't. Actually, that's what I have to say. I mean, there are always black sheeps among the farmers as well. So that's it. Also, most of the farmers know about those people who are doing that. And I also had some disputes with them that all are claiming that they're not doing it. But I like cycling, and I also like cycling in the winter. And I always have my mobile phone with me. And if I see those type of farmers fertilizing, I take a picture of their tractor, so I have the number plate, and then I can say, okay, I don't want that you lie to me. I just want to collaborate with you. If you lie to me, I just take my pictures to the next police, and then you are done. Because I mean, the number plate and the environmental conditions are all visible on this picture. But that's not my intention. The intention is to collaborate with them. And the more collaboration you have, the more input you get from their own business into your models, the better it is. So your model is definitely dependent on this transdisciplinary working field, where you not only include different sciences as you just outlined, but also to get information from the farmers, from lay people, what is going on. And that is sort of soft information, yes, but it's improving your model, because you know what is going on and what type of phosphorus, for instance, they are spraying out. We did some research in 2000, and I don't know, not we, but in the consortium where I've been, in 2006 or 7, where the processes of fertilization were analyzed. So you have this spraying table where the manure is just sprayed out in a huge swallow. Then you have these pipes which are moved to the underground, and then you have a sort of a system where the fertilizers is injected into the ground. And even these 3 types of fertilization processes made a big difference in the runoff of the nutrients. Meaning that this with the plate where the fertilizers is sprayed through the air first had a huge impact on the emissions, and everything which was injected into the system had really less impact to the aquatic conditions in terms of eutrophication. So all those smaller circumstances, how it was fertilized, when, also the process of fertilization, was it with the slope or 90 degrees of the slope? This is also important, because then if you build runoff pathways while fertilizing with the slope, well, then runoff is faster, and the faster the runoff is, the more material can transport, and the higher the impact is. So these are the small things which make the differences. Also, I mean, our main problem in our area is the buffer stripes. So we have no buffer stripe at all. So farmers are fertilizing into the slope of the riverbed. I mean, of course, then it's when the water level is increasing, it's immediately that the fertilizers are gone. But also the relation between slope steepness and buffer length. is a problem. I mean, if you have a very steep slope of 20 degrees or 25 degrees or a really steep slope, and you have a buffer stripe of 2 meters, it's useless. You have to have a minimum of 15, 20 meters to reduce the speed of the water and to let the fertilizer settle down. And then, of course, settling down is one process. Second process is that the fertilizers have to be taken up by plants. You should have like fast-growing plants coping with a lot of nutrients, where you can harvest the plants afterwards and transport them, for instance, for biogas production or whatever. So that was also, again, business-related action, because farmers then say, well, when I do a 20 meters of buffer stripe and I have a 1 kilometer field, I'm losing a decent amount of hectare. It's just, I'm just losing my money. So no, you're not losing your money. You just put something different there, which helps the environment, where you still can make money from. You just harvest the trees and bring them to gas production or whatever. So there was always discussion, but most of the farmers, they don't know about these opportunities. You have to tell them. And once you convince them doing it, and once there is only one trying that out and reporting, hey, that worked. I even got more money than before. Then everybody is doing it. But you have to have one doing this exercise. This is a lot of experiences, but yeah.
It's awareness raising and behavioral change. So yeah.
Fantastic.
So we have one question in the chat from Alexandra. She's asking, why are the records of weather conditions constantly being broken? Why do such changes occur so suddenly? And whether it is possible to monitor and control their strength with the help of GIS and climate system for supervision. Specifically, I mean sudden extreme climate events.
Yeah, I mean, these extreme climate events are still a challenge. I mean, the problem we have, particularly in our area, are these thunderstorms during the summer period, occurring because of heating up of the underground and the transport of the moisture to the atmospheric areas. And while the clouds are moving up, they're getting colder. Cold air cannot hold the water anymore, and then it comes back. These convective rainfall events. Like this 10 minutes cloud was also one of those convective rainfall events. These are very hard to predict. What you can predict, if you have greater weather construct where you know, okay, from the Atlantic there's coming a cyclone, and then you can predict it quite easily because you know the speed of movement and then it's there. These weather events I mentioned before are hard to predict, and I guess that they become more frequent because the heating up of the air on top of the ground is increasing because of climate change. We have all the years we have higher temperature values occurring. So now we also reached 40 degrees in Koppel, which we had never before. Particularly in our area, we have the challenge that we have a lot of surface water bodies. As I said, every 300 meters you reach statistically a surface water body. So there's enough water able to evaporate, and then of course the likeliness of those things are happening are bigger. Then we have the problem with the relief. I mean, in our case, if we have north-west weather situations, the clouds are moving towards the steep slopes, building the edge of the Alps. And they are just getting attached to the slope, and then we have the rainfall. But sometimes they even don't reach the slopes, but just move in front of the slopes. So just 10 kilometers, there's nothing, and then we have in the pre-alpine area, we have these sudden rainfall events. So we cannot really accurately predict what is happening in these 10 minutes intervals. So that's really a challenge. But what we could do is that we say, okay, we know all the other environmental phenomena, like if we know the soil water level, so the soil's moisture level is at a very high level. And even if it is not an extreme event, we'll still have surface runoff. And if we have a certain amount of rainfall, we can calculate and predict how much water is coming together at the confluence points of rivers in a certain time. And then we know if we reach a certain level, then the underlying municipalities will be flooded. And this is where I usually play with. I say, okay, I'm not particularly always looking at extreme events. I just look at other parameters as well, and then look, okay, even if just a bit of that is happening, then they will get flooded because all the other environmental parameters are like fully at full level. And this is where our predictions comes from. It's not only that there is an extreme precipitation event, but also taking into account other environmental parameters.
So thank you very much for this. I hope that everyone enjoyed the lecture. It was really nice. And I think that we should continue working together on these kind of problems. And also I think that UNSPMF has an assignment now to build a landscape lab for students to learning, so to study the processes, and probably in the future we will have something like that for our department. So thank you, Hermann, for being here today and for telling us what we can do in the future. So we have a homework to do. So thank you very much for being here, and thank you all for listening and for asking questions and participating. I would like to say that our lunchtime talk is now finished. So thank you again, and I really enjoyed it.
Okay, yeah, thank you, and have a nice day. So
you too. Bye bye.
Bye.
Bye bye. Thank you.
Thank you. Bye. Thank you very much.